All right. Well, I did always kind of promise you to have class outside. And while this class isn't really going to be outside, I thought we'd start out here. So I've been talking a lot to a lot of you about the past, not past thing. If you want to discuss that with me further, feel free to email me, set up a WebEx meeting, whatever. Um, but in the process, it was pointed out to me that these video lectures had kind of lost some of the zip that in-person lectures used to have, and even the earlier videos used to have. So I thought, especially after the comment that I was trying to shoehorn this into the people and blogs thing, no shoehorn. We're just going to cannonball right into the deep end and ruin Aunt Ethel's weave, okay? Right. So here we are, my backyard. I'll show you where I've been spending all my time early in the morning. Into the garage. I don't even know if you can see it. There it is, folks. That's the lattice board. It's a torture device of sorts because I can't go to the climbing gym anymore. And we're not going to walk through the house because I haven't cleaned the kitchen. This is the driveway, which now contains all the stuff in the garage that is less important than the climbing wall. These are all the bikes that haven't been stolen yet. And this is the door to the basement where the magic happens. Ooh, we almost forgot. We do have to go up here. Still avoiding the kitchen. Because it was also pointed out to me that I was a little remiss in keeping up on the heavy rotation. So, this right here is Donna Summer, Love Trilogy. A disco classic. And the other two I was going to put on the list for today are also monstrous classics. For $5 from the West Lafayette Public Library record sale, Kiss, Destroyer, can't live without that. And Run DMC, Raising Hell. Alright, so those are my recommendations for now. I'll have one more when we get downstairs, unless I forget. Alright. The home medieval gym torture area is expanding. We got some rings now. We got some pulleys, ropes. Just missing the Iron Maiden. Here it is. Okay. There we go. There. All right. So today we are on chapter 4. And it occurred to me that in making these notes, I'm actually doing exactly what you should be doing to study for the final exam. This whole process of just writing down the high points and forcing yourself to go through every chapter and write down the definitions. Don't just read them. Okay? It is a well-known fact that the more senses you use to absorb a piece of information, the more likely you are to remember it. Therefore, you read it, you write it down, and you say it to yourself like a crazy person. Okay? But writing down these notes like I've been doing is almost a disservice to you because then you're just going to go online and read them and feel like you've done the right thing. No. You should go online, read them, and then try and write them down from memory. Then you'll be all set. Okay, we're on chapter 4. And that is on limits of functions. Okay? So the very first thing to define here is the notion of a cluster point. Right? So if A is a subset of the real numbers, then C, a real number, is a cluster point of A if for all epsilon greater than 0, the neighborhood, the epsilon neighborhood around C, even after you throw out C itself, intersected with A, is not empty. Whew. Which is notationally kind of a lot. But what it's really saying is, okay, C is a cluster point of A if, no matter how small a distance you give me, I can always find something from A which is that close to C, and which is moreover not equal to C. That's all this is saying. Okay, you can get really, really close to C, as close as you want to C, using points of A that are different from C. So that is a cluster point. Okay, so I was also mentioning, and it also sort of came to mind in passing, that these short answer questions, right? Again, I am extremely unlikely to just start asking definitions. Okay, so I'm probably not going to ask you what is a cluster point of a general subset A of the real numbers. What I am much, much more likely to ask you is, what are the cluster points of the following set A? Okay, so I'll give you a little chart here to remind you of a few examples, but I would highly recommend that you work out for yourself why these are true. Okay, and if you can convince yourself that these are true, then you should be well prepared to prove that certain other sets have certain cluster points. So here's the set A on the one hand, and cluster points on the other hand. So you could consider the open interval from 0 to 1. And the cluster points of that guy turn out to be the closed interval from 0 to 1. You can also take the closed interval from 0 to 1. And the cluster points of that guy are also the closed interval from 0 to 1. You could also take the finite set consisting only of 2 points, 0 and 1. Okay? And the set of cluster points there is empty. And indeed, the set of cluster points for any finite set is empty. Okay? And then finally, let's take the rational numbers. The cluster points there turn out to be all of the real numbers. Because, of course, thanks to the density theorem, given any real number, you can get as close as you want to that real number through a rational number, and even through a rational number not equal to the original given real number. Okay, so there are some examples of sets and the cluster points. What next? Okay, so now we have the definition of the limit. This is one definition that I will allow, I will ask. I promised I would ask this on the final, and even though you'll be able to look it up, I'm still going to ask it on the final. Because it's some kind of like experiment at this point, right? I mean, in the past, I have tried and told people, this is the first question on the test. I'm just going to ask you to regurgitate the definition of the limit. I tell them the answer, I tell them the answer, and still I have yet to find the class that actually gets it right, universally, right? So this time, not only am I telling you that this definition is going to be the first question 1A for 5 points, you're also going to have 24 hours to look it up in a book or on Google or wherever. And I'm really honestly curious to see if somebody still gets it wrong. And, You won't ever know who you are, but I'll wonder about you if you do get it wrong forever. Okay. So, f, a function from A to R, C, a cluster point of A. The limit as x approaches C of f of x is equal to L if for all epsilon greater than 0, there exists a delta greater than 0 such that the distance from f of x to L is less than epsilon if the distance from x to C is greater than 0, meaning that x is not equal to the cluster point, but is less than delta, meaning that x is not further away from the cluster point than delta. Okay, there it is. Question 1A for 5 points. So that, together with the 20-point head start that I'm giving you in the long answer section, means that out of 200 points, basically 25 of them are guaranteed. Okay, so come on, you can do this. Oh, right, so I did send out an email, but just the university sent me this email. If you really want to know what they mean by this, you'll have to ask them more directly. But they did say that their impression of a passing grade means C- or better. So if you switch to a pass-fail situation, then faculty are expected only to give passing grades to people with C- or better. Meaning that, really, technically speaking, you could get a D, which I would normally consider to be a passing grade, and still fail if you switch to pass-fail. So, something to think about. All right, so there's the definition of the limit. Limits are unique. Okay, so if the limit is equal to L and the limit is equal to L prime, then L equals L prime. I mean, there's only, if there is a limit at all, then there is only one limit. Okay? Much more important than that is the so-called sequential criterion. For limits. Okay, so that says the following are equivalent. 1, the limit as x approaches a cluster point C of the domain of f of x is equal to L. And 2, if xn is a sequence in the domain A, xn converges to C, and moreover, each xn is not equal to C, then we have f of xn converges to L. Pardon me. Okay? So this means that you can couch the statement that the limit is equal to L entirely in terms of sequences. So the notion of convergence here can be reduced entirely to understanding convergence of sequences. This limit is equal to L if and only if every time you have a sequence in the domain converging to the cluster point and such that each element in the sequence is not equal to the cluster point, then you moreover have that f of that sequence converges to L. Well, that's the same thing as the limit being L. Okay? So that is the sequential criterion for the limit of a function. Which lends itself then to the introduction also of a divergence criterion. Okay, so just as you may like to know when the limit as x approaches c of f of x is equal to L, you might also like to know when that limit is not equal to L. Okay, so that's divergence criterion. Okay, and it says that the limit as x approaches c of f of x is not equal to L if and only if there exists a sequence xn in the domain such that xn converges to c and all the xn's are not equal to c, yet the sequence of function values, the f of xn's, does not converge to L. Okay? So, if you would like to say, sometimes this is useful, you want to know that the limit is not equal to a certain number, it's enough to find some sequence converging to the point you're interested in, consisting of points not equal to the point you're interested in, which is usually not too hard, right? Such that when you apply f to that sequence, it doesn't converge to L. Okay? That's enough to say that this limit is not equal to L. So there is the divergence criterion. And I mean, as a kind of meta comment, chapter 4 is not particularly long, or, you know, when it comes right down to it, not particularly novel, in that once you have introduced this sequential criterion for what it means to have the limit of f of x be equal to L, then really all the interesting theorems about limits of functions are reduced to the similar theorems about limits of sequences, which we already know and have already established in chapter 3, which was kind of a doozy. Right, which brings us to, then, section 4.2, limit theorems. Okay, so so as I just finished explaining, right, this theorem, the limit theorem here, for combinations of functions, basically just follows from the same theorem for sequences. Okay? So, let's see. Let's say that f and g are functions from A to R. Alpha is some real number, and C, cluster point of A. And finally, the limit as x approaches C of f is equal to L, and the limit as x approaches C of G is equal to, say, M. Okay? Then what is true? Well, 1, the limit as x approaches C of f plus G is equal to L plus M. 2, the limit as x approaches C of f times G is L times M. 3, the limit as x approaches C of alpha times f is alpha times L. And finally, 4, the limit as x approaches C of f over G is equal to L over M if m is not equal to 0. Okay? So these are all things you should know already, but we're writing them down anyhow. Let's see, what else? All right, the other one I wanted to mention was, of course, the Squeeze Theorem. And to clarify something about the Squeeze Theorem that was asked about earlier in the semester, so Squeeze Theorem, right? So we'll let f, g, and h be functions from A to R, and C a cluster point of A. And the idea, of course, is that the function g is going to be sandwiched in between f and h, right, through inequalities, and then we're going to insist that the limit of the two guys on the outside, the f and the h, those two limits exist and are equal, and they then force the limit in the middle, the limit of g, to be equal to what the other two limits are equal to as well. And then the question I got earlier in the semester was, well, to what extent does it really have to be true that f is less equal to g is less equal to h? Does it have to be true everywhere? And the answer is no. It only has to be true on some little teeny tiny neighborhood of C. As long as it's true that when you get really close to C, you have these inequalities, that's good enough. So we're going to let these three functions have domain A. C is a cluster point of A, and then we will say that f of x is less equal to g of x is less equal to h of x for all x in some little neighborhood of C intersect A. Okay, so saying if you get really close to C, then these inequalities hold, okay? And then the conclusion is that if the limit as x approaches C of f of x is equal to the limit as x approaches C of h of x is equal to L, then the limit as x approaches C of g of x must also be equal to L. Okay? So that's the Squeeze Theorem with this little bit about the extent to which these inequalities have to hold clarified, I hope. All right. And that pretty much, once again, the proof of the Squeeze Theorem for limits of functions follows from the proof of the Squeeze Theorem for limits of sequences, which we've already covered in our review of Chapter 3. Okay. Right, so, right, I promised, one more thing for this heavy rotation. And this one's kind of a cheat, but I think worth it. So it's actually a whole it's a whole collection of compilations. So they're entitled Late Night Tales. Okay? And in each case, some, okay, I'm not going to say well-known outfit, but some, like reasonably well-known band is asked to pick what they might listen to on a chilled out late night. So each one of these albums is a compilation, but this is really like the ne plus ultra of compilations. I mean, these things are fantastic. So not only is there a whole shopping list of interesting artists to listen to in their own right who make these compilations, but then you get to listen to what they in turn are listening to. So you're like 17 levels of super cool obscurity down. And there are some real fascinating gems in there. So some of the artists that compile these, not the artists that are actually on the compilations, but the people compiling them are like, I don't know, there's Air, there's Groove Armada, I think there's one by Snow Patrol, I think the Flaming Lips are on there. I think Belle and Sebastian are on there. Anyway, there are about like 20 or 25 of these, but I mean, and they're all a little different, and they might not be everyone's cup of tea, but definitely fantastic late night and/or Sunday afternoon music. Okay, all right, and then finally for chapter 4. We have section 4.3, which is entitled Extensions of the Limit, or extensions of the concept of the limit. I don't know exactly what they call it. Essentially, this section consists of 3 definitions, and each of those 3 definitions has 2 different sort of obvious parts, okay? So the first one is, what does it mean to take the limit from the left or the right? The second one is, what does it mean for the limit to go to plus infinity or minus infinity? And the last one is, what does it mean for the limit to exist as x goes to plus infinity or minus infinity? So 3 definitions, each with 2 flavors. So let's start with the first one. So the limit as x approaches c from the right of f of x is equal to L if for all epsilon, for all epsilon greater than 0, there exists a delta greater than 0 such that f of x minus L is less than epsilon if... So far, aside from this little plus up here, this looks exactly like the definition of the limit. The difference comes at the very end where we insist that 0 be less than... Now we want x to be a little bigger than c. So we're going to ask for, instead of just the absolute value of x minus c to be bigger than 0, we're going to ask for x minus c itself to be bigger than 0 and still less than delta. Okay? So that's what it means to take the limit from the right. The only change comes at the end here, and all we do is get rid of the absolute value brackets on x minus c and insist that x minus c be bigger than 0, okay, in order to come from the right. Now, to do the limit from the left is a very minor adjustment. So first of all, we replace the plus with the minus, and then everything else is the same, except now this little inequality here tells me that x is bigger than c. Now I want x to be less than c, right? That means that it's c minus x that is greater than 0 instead of x minus c. Okay, so again, you drop the absolute value brackets, but then you replace the absolute value of x minus c with c minus x. Okay? So that's the limit from the left and the limit from the right. Okay. We can probably recycle some. So that's the limit from the left, limit from the right. Now, let's look at infinite limits. So what does it mean for the limit as x approaches c to be equal to infinity? So what's going to change this time is what happens with the function. Okay, so the limit as x approaches c of f of x is infinity if for all, let's say, capital M greater than 0, to lend the impression of size here, there exists a delta greater than 0 such that now we want f of x to be greater or equal to m if, and now we're back to our absolute value of x minus c is less than delta. Okay? So given any really big positive number, you can get close enough to c so that the function is always bigger than or equal to this given positive number. Okay? All right. So that's plus infinity, and then unsurprisingly, we've got its cousin, minus infinity. So the limit as x approaches c of f of x is minus infinity if for all m less than 0, there exists a delta greater than 0 such that f of x is less than or equal to m if, once again, the absolute value of x minus c is bigger than 0 and less than delta. Okay? So that's 4 of the 6 definitions. Now for the last 2, the thing that changes here is that we're back to having a limit which is equal to a number. It's equal to L. But now the c changes. Instead of c, we're going to have plus infinity. Okay, so the limit as x approaches infinity of f of x is equal to L if for all epsilon greater than 0. Now we're going to say there exists an m greater than 0 such that, and we'll throw out this whole last line here. Right, so here the epsilon is greater than 0 because we're going to want f of x to be close to L. And this capital M is going to tell us how far out x has to be. Okay, so if for all epsilon greater than 0, there exists an m greater than 0 such that the distance from f of x to L is less than epsilon if x is greater than m, or greater than equal to m, doesn't matter. Okay? Right, so the distance from f to its limit is small if x is big enough. That's what it means to have the limit as x approaches infinity of f of x be equal to L. Okay. And finally, what happens with minus infinity? So this is a minor variation on a theme. As x approaches minus infinity, the limit of f of x is L if for all epsilon greater than 0, there exists an m less than 0, such that once again the distance from f of x to its limit L is small if x is less than or equal to m, if x is big enough in the negative direction. Okay? And those 6 definitions are the content of section 4.3. Okay? All right. Well, that's it for Chapter 4. I will post those notes and, of course, this video. And then tomorrow, hopefully, I will get through Chapter 5. And I guess since there's only really, we'll see. I guess Chapter 5 is kind of substantial, so I might do it in 2 parts. But Chapter 5, and then we've just got the first section of Chapter 6. So certainly by Friday, all the review notes and videos will be up. And reminder then that the final exam will be available on Gradescope at 9 a.m. Eastern Daylight Time on Wednesday, May 6th, and must be submitted by 9 a.m. Eastern Daylight Time on Thursday, May 7th. All right, stay safe out there and wash your hands. Okay, bye.